Let us now attempt to unify our previous discussions of energy and power and efficiency with our newfound appreciation of electrical power. Let's first review power and energy. As you are no doubt aware, power is energy over time. Algebraic permutations of this three-variable relationship also suggest that energy is power times time, and time is energy over power. Officially, energy is expressed in units of joules, although in practice, the unit of kilowatt hours is a more practical unit of energy, where 1 kilowatt hour is equivalent to 3.6 megajoules. If you've been following this lecture series in its intended order, you should already have some level of familiarity with energy and power. As such, let's roll right into an illustrated example. Consider a device that operates on 80 volts DC and draws 4 amperes of current. Let's say this device runs for 12 hours a day. How much energy in units of kilowatt hours does it consume every day? This is a two-stage problem. First, we need to determine the power rating of the device. Then, given this power rating, we need to determine the energy consumed after 12 hours of use. Power is voltage times current. 80 volts times 4 amps yields 320 watts of power. Energy is power times time. 320 watts times 12 hours yields 3,840 watt hours, or more appropriately, roughly 3.8 kilowatt hours. Too easy. Let's put your understanding of more sophisticated energy and power calculations to the test with a set of example problems. Given known values for each scenario, see if we can solve for the desired properties using the most efficient and direct means possible. Express all answers in proper engineering format to the 10th place. Express energy in units of kilowatt hours. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem features a device that operates off a 120 volt DC, known to consume 5 kilowatt hours of energy after 8 hours of use, and we're being asked to solve for the power rating of the device and the anticipated amount of current draw. Power is energy over time. 5 kilowatt hours over 8 hours yields a power rating of 625 watts. Current is equal to power divided by voltage. 625 watts divided by 120 volts yields an anticipated current draw of roughly 5.2 amps. Our next problem features a device modeled as a 120 ohm resistor intended to operate using 60 volts DC, and we're being asked to solve for the power rating of the device and determine how much energy the device uses over a span of 16 hours in units of kilowatt hours. Power is equal to voltage squared divided by resistance. 60 volts squared divided by 120 ohms yields a power rating of 30 watts. Energy is power times time. 30 watts times 16 hours demonstrates the device consumes 480 watt hours, or more appropriately, roughly 0.5 kilowatt hours of energy. Finally, our last problem features a device that needs to accomplish a task that necessitates the expenditure of 1.2 kilowatt hours of energy, and it needs to happen over a 30-minute time span. In doing so, the device is anticipated to draw 8 amps of current. We're being asked to solve for the power rating of the device and the supply voltage necessary to operate the device. Power is energy over time. 1.2 kilowatt hours over 30 minutes, or 0.5 hours, yields a power rating of 2.4 kilowatts. Voltage is equal to power divided by current. 2.4 kilowatts divided by 8 amps demonstrates the device necessitates 300 volts to operate. Let us now review efficiency and its relationship to electrical power. As you are no doubt aware, efficiency is the ratio of usable power output over input and is typically expressed as a percentage. Previously, I asserted that power input to a system is always equal to power output. You might therefore be under the mistaken assumption that all systems are 100% efficient. This is undoubtedly untrue. However, it is true that all input inevitably goes somewhere, useful or otherwise. The truth can be found in the qualifier useful output. Allow me to demonstrate by way of a series of illustrated examples. Consider a 100 watt incandescent bulb and a 25 watt LED bulb, both designed to operate using 120 volts. Let's say both bulbs yield an equivalent amount of useful output in the form of 5 watts of radiant power. The efficiency of the 100 watt incandescent bulb is 5 watts of usable output over 100 watts input, which yields an efficiency rating of 5%. This is super crappy. Similarly, the efficiency of the 25 watt LED bulb is 5 watts usable output over 25 watts input, which yields an efficiency rating of 20%. This is still pretty crappy, but not nearly as crappy as the incandescent bulb. Let's say we use these bulbs for 4 hours a day, 365 days a year. This amounts to an annual usage of 1,460 hours. Energy is power times time. Over the course of a year, the 100-watt incandescent bulb consumes 146,000 watt-hours, or more appropriately, 146 kilowatt-hours of energy. Over the course of the same year, the 25-watt LED bulb consumes 36,500 watt-hours, or more appropriately, 36.5 kilowatt-hours of energy. If a user was charged, let's say 12 cents per kilowatt-hour, operating the 100-watt incandescent bulb for 4 hours a day for a year would cost $17.52, whereas operating the 25-watt LED bulb for 4 hours a day for a year would cost only $4.38. The greater than $13 differential more than justifying the cost to upgrade to the more efficient 25-watt LED bulb. As if this was not enough, consider the current drawn by these different bulbs while in operation. Current is power divided by voltage. 100 watts divided by 120 volts demonstrates the 100-watt incandescent bulb draws roughly 833.3 milliamperes of current. Similarly, current is equal to power divided by voltage. 25 watts over 120 volts demonstrates the 25-watt LED bulb draws only roughly 208.3 milliamperes of current. As this example is intended to illustrate, this really highlights the clear superiority of the more modern efficient LED bulb over the hopelessly inefficient incandescent bulb. Not only does the LED bulb use less energy over time, thereby costing the operator less, it also draws less current. This may not seem dramatic. However, consider the design and construction of the electrical infrastructure meant to support a large number of facilities, all drawing smaller amounts of current. Given a reduction in current requirement, the size of the wiring, thus the weight and expense of the larger transmission system, can also be smaller. Here's another illustrated example of efficiency intended to differentiate between usable output and input. In a perfect world, batteries are ideal voltage sources with no internal resistance. In the real world, small imperfections negatively affect performance, and some output can be considered loss. Consider a real-world 12-volt battery, modeled as a 12-volt source in series with a small internal resistance of, let's say, 2 ohms, intended to supply an electrical load modeled as a variable resistor currently set at 60 ohms. You know, the gray box surrounding the battery and internal resistance is meant to imply that the internal resistance is part of the battery and cannot be isolated from it. Let's say any and all power consumed by the 60 ohm electrical load is considered directed towards useful output, and any power consumed by the internal resistance of the battery is considered a loss. The source needs to supply power to both elements. It can be said that power supplied by the source, i.e. power input, is equal to power consumed by the internal resistance plus the power consumed by the electrical load. Power in would equal power out. However, only one of the power outputs is considered useful, whereas the other considered a loss. This problem necessitates an understanding of series circuit properties, a topic we'll examine at length in later lectures. So for the purpose of today's lecture, I'll do the larger series analysis for you. That way you can concentrate on the 3 individual elements constituting the system: the source, the internal resistance, and the electrical load. Follow along as best as you can. The 12-volt source sees the series combination of the 2 ohm internal resistance and the 60 ohm electrical load for a total resistance of 62 ohms. Current is equal to voltage divided by resistance. Ohm's law demonstrates the source would provide roughly 193.5 milliamperes of current. Power is equal to voltage times current. The power input to this system is 12 volts times 193.5 milliamperes, or roughly 2.3 watts. 193.5 milliamperes of current travels through both the internal resistance and the electrical load. It can be said source current equals current through the internal resistance, which equals current through the electrical load, which all equals 193.5 milliamperes of current. Given the direction of conventional current travel, we should expect a voltage drop across the internal resistance, positive to negative, bottom to top, and a voltage drop across the electrical load, positive to negative, top to bottom. Let's determine the voltage drop and the power dissipated by the internal resistance first. Voltage equals current times resistance. An application of Ohm's law demonstrates the internal resistance experiences a small voltage drop of roughly 387.1 millivolts. Power is equal to voltage times current. The power consumed by the internal resistance is 387.1 millivolts times 193.5 milliamperes, or roughly 74.9 milliwatts. This small amount of power would be considered a loss to this system. Let's now determine the voltage drop across and the power consumed by the electrical load. Voltage is equal to current times resistance. An application of Ohm's law demonstrates the electrical load experiences a roughly 11.6 volt drop. Power is equal to voltage times current. The power consumed by the electrical load is 11.6 volts times 193.5 milliamperes, or roughly 2.2 watts. This would be considered useful power output. If we examine the efficiency of the complete system, of the roughly 2.3 watt input into the system, roughly 2.2 watts is directed towards usable power output, and only 74.9 milliwatts is considered a loss. This results in an efficiency of roughly 96.8%. Not bad. You note at the present operating condition, the electrical load only experiences roughly 11.6 volts of the available 12 volts due to the small drop across the internal resistance. This is what is known as the working voltage of a battery, which is in contrast to its nominal or nameplate rating of 12 volts. Given any power consumed by the internal resistance is considered a loss, we would expect the battery to exhibit some small degree of temperature rise, accounting for this inefficiency. Keep in mind these figures are snapshots of the system in its present configuration, and different operating conditions may yield different results. For example, consider the same battery modeled as a 12-volt source in series with a small internal resistance of 2 ohms. Only this time, the electrical load is a smaller resistance of 20 ohms. Let's examine this system in this present configuration and use our previous analysis as a basis of comparison. As previously, since we've yet to discuss series circuit properties, I'll do the larger series circuit analysis for you. That way you can concentrate on the power analysis of the 3 individual loads constituting the system: the source, the internal resistance, and the electrical load. Again, follow along as best as you can. The 12-volt source sees the series combination of the 2 ohm internal resistance and the 20 ohm electrical load for a total resistance of 22 ohms. Total resistance went down. Current is equal to voltage divided by resistance. Ohm's law demonstrates the source would provide roughly 545.5 milliamperes of current. Given total resistance went down, it is entirely understandable current went up. Power is equal to voltage times current. The power input to the system is 12 volts times 545.5 milliamperes, or roughly 6.5 watts. Given current went up, it is understandable that input power also went up. 545.5 milliamperes of current travels through both the internal resistance and the electrical load. As previously, it can be said source current equals current through the internal resistance, which equals the current through the electrical load, which equals 545.5 milliamperes. Given the direction of conventional current travel, we should expect a voltage drop across the internal resistance, positive to negative, bottom to top, and a voltage drop across the electrical load, positive to negative, top to bottom. Let's determine the voltage drop across and the power dissipated by the internal resistance first. Voltage equals current times resistance. An application of Ohm's law demonstrates the internal resistance experiences a roughly 1.1 volt drop. Given current through the internal resistance went up, it is understandable the voltage drop across it also increased. Power is equal to voltage times current. The power consumed by the internal resistance is 1.1 volts times 545.5 milliamperes, or roughly 595 milliwatts. This is considered a loss to this system. Given both current through and the voltage drop across the internal resistance went up, it is doubly understandable that power consumed by the internal resistance went up. The power consumed by the internal resistance might be directed towards a slightly higher degree of temperature rise, accounting for this inefficiency. Let's now determine the voltage drop across and the power consumed by the electrical load. Voltage equals current times resistance. An application of Ohm's law demonstrates the electrical load experiences a roughly 10.9 volt drop. You note at the present operating condition, the working voltage of the battery is dropped. This explains why the lights sometimes dim when you start a car driven by an internal combustion engine. The tremendous surge of current drawn by the starter motor temporarily results in a reduction of working voltage to all elements in the system. Power equals voltage times current. The power consumed by the electrical load is 10.9 volts times 545.5 milliamperes, or roughly 6 watts. This is to be considered usable power output. If we examine the efficiency of the complete system, of the roughly 6.5 watt input into the system, roughly 6 watts is directed towards usable power output, and roughly 595 milliwatts is directed towards losses. This results in efficiency of roughly 90.9%. Still not bad. However, you'll note at the present operating condition, it is less efficient than it was previously. This is to imply that properties like efficiency and working voltage are not static figures, but are rather dependent upon operating conditions. At the present operating condition, the battery is delivering more power to the electrical load. However, a larger portion of this input is being misdirected towards losses than previously, thus the lower efficiency rating. We'll have ample opportunities to examine batteries in more detail in later lectures. For now, you should simply appreciate that power can be calculated for individual elements, and for a larger system, all power input is inevitably directed towards some output, useful or otherwise. Additionally, you should be able to calculate efficiency and energy figures and understand how these properties relate to electrical power. Let's now examine electrical power transmission. In a perfect world, a source would deliver all power to an intended destination with no losses along the way. In the real world, the means of transmission itself extracts a degree of losses. In an effort to minimize losses in the lines, electrical power is ordinarily transmitted from a source to a destination using high voltage rather than high current. Ordinarily, this is done with AC electricity, a type of electricity that cyclically varies polarity and magnitude rather than DC. AC is its own weird beast, which we'll examine in greater detail in later lectures, but for the sake of this introductory discussion, let's just pretend they're equivalent. Consider a generator out in the sticks, operating at 700 volts DC, trying to transmit 2 megawatts of power to some distant city located in the shoe-wearing regions of the country using a 300-mile-long transmission line modeled as a resistor with 0.15 or 150 milliohms of resistance. This might not seem like much resistance, and you may instinctively presume that the line losses will be minimal. However, this is far from the truth. I must remind you that power is equal to current squared times resistance. Even a small resistance carrying large amounts of current will dissipate tremendous amounts of power. In this case, any power dissipated by the transmission line would be considered a loss. This generator is producing 2 megawatts, 2,000 kilowatts, or 2 million watts. This would be considered the input to the system. If current is equal to power over voltage, if you tried to transmit all 2 megawatts of power using 700 volts, this would necessitate the transmission line carry 2 megawatts over 700 volts, or 2,857.1 amps, or roughly 2.9 kiloamps of current. This is an astronomically large amount of current. An application of the power equation, where power equals current squared times resistance, demonstrates the line will dissipate 2.9 kiloamps squared times 0.15 ohms, or 1,224,489.8 watts, or more appropriately, roughly 1.2 megawatts of power, more than half the power being sent by the 2 megawatt generator, leaving only 775.5 kilowatts for the distant city to put to good use. Long story short, the generator makes 2 megawatts, or 2,000 kilowatts, but the city only gets 775.5 kilowatts. This scenario results in an extremely poor efficiency rating of only 38.8%. A majority of the generator's power input is expended not in powering the distant city, but rather in turning the transmission line into a 300-mile-long toaster. This cannot and will not work. High current results in massive amounts of line losses, and substantially less input is directed towards useful output. It is largely for this reason electrical power is generated and transmitted using AC rather than DC. AC electricity, in contrast to DC, allows for the use of a device known as a transformer that steps up voltage at the same time stepping down current, and vice versa. We'll examine AC power and transformers in later lectures. Consider the same 2 megawatt generator transmitting power to the distant city along the same transmission line modeled as a 150 milliohm resistor, not at 700 volts, but rather at 35 kilovolts, or 35,000 volts, 50 times greater than previously. How will this marked increase in transmission voltage affect the efficiency of this system? Given current is equal to power over voltage, if all 2 megawatts of power were transmitted using 35 kilovolts, this would necessitate the transmission line carry 2 megawatts over 35 kV, or 57.1 amps of current, i.e. 50 times less than previously. By stepping up voltage, we can transmit the same amount of power using substantially less current. Let's examine losses in the transmission line. An application of the power equation, where power is equal to current squared times resistance, demonstrates the line will dissipate 57.1 amps squared times 150 milliohms, or roughly 489.8 watts, of the available 2 million watts for the distant city to put to use. Long story short, the generator makes 2 megawatts, or 2,000 kilowatts, or 2 million watts, and the city gets 1,999,510.2 watts, for all intents and purposes, all 2 megawatts. This scenario results in a much better efficiency rating of 99.98%. One more short example before we bring this lecture to a close, this one intended to illustrate how extremes of voltage and current affect power calculations. Consider a photovoltaic panel, or a PV panel, PV panels are characterized by something known as an IV curve, where voltage is on the horizontal axis and current is on the vertical axis. As a simplification, increasing levels of light intensity increase current output of a solar panel. At an intensity of 200 watts per meter squared, the IV curve might look something like this. At an intensity of 400 watts per meter squared, the IV curve might look something like this. Light of increasing in intensity yields a similar pattern up to something known as standard temperature and conditions, or STC, whereby the panel is illuminated by light of a standard intensity of 1000 watts per meter squared. This is the performance standard used by most panel manufacturers to rate their product. When you buy a 300 watt solar panel, it means it produces 300 watts when it is exposed to light of 1000 watts per meter squared intensity. This is what is known as the maximum power point, meaning it is the most ideal scenario where power is at a maximum. As you're no doubt aware, power is the product of voltage and current. Maximum power does not necessarily mean maximum voltage nor maximum current, but rather maximum power is an occasion in which the product of voltage and current is at a maximum. PV panels often include a datasheet which specify the voltage and current at the maximum power point. For example, consider a panel that produces 300 watts at STC with the following characteristics. At the maximum power point, voltage is known to be 32.48 volts, and current is known to be 9.24 amps. Power is equal to voltage times current. 32.48 volts times 9.24 amps yields roughly 300.1 watts of power. What do we make of the other data points on the IV curve where the solar panel is operating at less than maximum power conditions? For example, consider the open circuit voltage, where voltage is respectively high at 40.45 volts. This would be the far right side of the IV curve at this given intensity. As the title open circuit implies, the panel does not have a conductive path and no current flows. Power is equal to voltage times current. 40.45 volts times 0 amps yields 0 watts of power. Additionally, consider the short circuit current, where current is respectively high at 9.91 amps. This would be the far left side of the IV curve. As the title short circuit implies, the panel does have a conductive path, however, no voltage exists. Power is equal to voltage times current. 0 volts times 9.91 amps yields 0 watts of power. You'll note both extreme occasions, open circuit conditions with maximum voltage and 0 current, and short circuit conditions with maximum current and 0 voltage, yield output not just less than maximum power, but 0 power. If we multiply voltage and current for all points on the IV curve and overlay a plot of power in the same graph, we'd observe something like this. The power curve goes from 0, climbs to some maximum, peaks out, and begins to fall, where the maximum power point is the ideal scenario in which power, the product of voltage and current, reaches a maximum, in this case, roughly 300 watts. Alright, one last thing, I promise, before we close up shop. As I mentioned earlier, the measurement of power necessitates a technician choose between 3 available options. First, a technician could take a voltage reading using a voltmeter, then take a current reading using an ammeter, then multiply the voltage and current reading together to obtain a power figure in units of watts. Second, given a known resistance, a technician could take a single voltage reading, then square voltage and divide it by resistance to obtain a power figure in units of watts. Finally, given a known resistance, a technician could take a single current reading, then square current, and multiply by resistance to attain a power figure in units of watts. A fourth method exists using a device known as a wattmeter. A wattmeter is a special purpose instrument designed for single-step measurements of power where no calculation is necessary. One can visualize a wattmeter as a box or a bridge with 2 meters inside. One measures current and the other measures voltage. Internal circuitry performs a multiplication operation and a result in units of watts is displayed as an output. Typically, a DC wattmeter is installed as a 2-input, 2-output bridge between a source and a load. 2 input terminals, ordinarily labeled line, are connected to the source terminals, and 2 output terminals, ordinarily labeled load, are connected to the load. Arranged in such a fashion, the ammeter portion of the wattmeter measures current from the source through the load, and the voltmeter portion measures voltage across the load. Sometimes you might see 3-terminal wattmeters, where the bottom terminal serves as a common terminal to the input and output pair. Importantly, consider the placement of the meters internal to the wattmeter. Voltage is measured across something, whereas current is measured through something. The wattmeter just serves as a single bridge between our input and output if our only measurement concern is wattage. That's all I've got for you today regarding power. This single topic tied together a number of previously unrelated topics, and it is entirely understandable and encouraged that you revisit this topic if necessary. Moving forward, realized progress will be predicated upon your understanding of previously covered material. In this basic lecture, you've already gotten an appreciation of how power calculations are directly related to high-level topics like power transmission and photovoltaic systems, and this level of interconnectedness will only become more important as we progress through this series. In conclusion, this lecture took a close look at the different permutations of power calculations for DC power, sometimes collectively known as Watt's laws. We additionally reviewed power and energy and efficiency calculations and introduced a common device used to measure power, the wattmeter. Additionally, we had a preliminary discussion of the importance of power calculations related to the transmission of power and alternative energy sources. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.